Properties of cyclic groups. A group G is called cyclic if there is an element A in G such that G is equal to the set of all integer powers of A. Such an element A is called a generator of G. So, G is cyclic if G is equal to the cyclic group generated by A. Example 1. The set of integers Z under ordinary addition is a cyclic group. It has only two generators, 1 and -1. Example 2. The set Zn is the set of numbers from 0 to n-1, all these integers. Here n is greater than or equal to 1, a positive integer. And the operation in this group is addition mod n. Here again 1 and -1 are generators, but this group may have more generators depending on the particular value of n, as we'll see later. Theorem: let G be a group of let A belong to G. If A has infinite order, then A to the I is equal to A to the J for two integers I and J, if and only if I is equal to J. If A has finite order, say n, then the cyclic group generated by A consists of these powers of A from 0 to n-1, and A to the I is equal to A to the J for two integers I and J, if and only if n divides I minus J. To prove this, the first case is obvious, so we prove the second case, and the order of A is n. The cyclic group generated by A consists of these elements, and for any q, integer q, and for r between 0 and n-1, this is equal to A to the r. So, the set of all integer powers of A is just this set over here, and the order of the number of elements in this set is n, obviously. So, from this equality over here, two integer powers of A are equal if and only if I and J have the same remainder when divided by n, which means that their difference is divisible by n, and also this means that I and J are congruent mod n. Corollary 1. The order of the element A is equal to the order of the cyclic group generated by A. Both are equal to n. Corollary 2. A to the k is equal to E if and only if the order of A divides k. Here k is an integer. This follows from the fact that E is equal to A to the n when A has order n, or A to the 0. So k and 0, A to the 0 is E. k and 0 must be congruent mod n, which means n divides k. Now we'll prove this important theorem. Let A be an element of order n in a group, and let k be a positive integer. Then the cyclic group generated by A to the k is equal to the cyclic group generated by A to the power the GCD of k and n, and the order of A to the k is this n divided by the GCD of n and k. The proof: here we denote the GCD of n and k by d, so this exponent here is d and this denominator is d. Then k is divisible by d, so we can write that k is equal to d times some integer r. Then a to the k is a to the d to the r, which shows that a to the k is contained in the cyclic group a to the d, generated by a to the d, and any power of a to the k is contained in the cyclic group generated by a to the d. So we have this inclusion. Now we want to prove the opposite inclusion, and then we'll have equality. Let s and d be integers such that the GCD d of k and n is written as a linear combination like this. We know that this is always possible. Then a to the power d is a to the n d times a to the kd, but a to the n is 1, so we get a to the equals a to the kd. This shows that a to the d is contained in the cyclic group generated by a to the k, and any power of a to the d must be in that group also, because any group is closed under the operation. This is the opposite inclusion of this. Having both, we have equality. Because these groups are equal, they have the same number of elements. And the number of elements is in the group is equal to the order of the generator. The order of a to the power d is n to the n divided by d, because d is a divisor of n. And this is exactly this equality that we want to prove. And we also prove the previous equality. Corollary: orders of elements in finite cyclic group. In a finite cyclic group, the order of an element divides the order of the group. Corollary 2: let A be an element of order n, then the group generated by a to the I is equal to the group generated by a to the j, if and only if the GCD of n and I is equal to the GCD of n and j. Here I and j are some integers. And the order of a to the I is equal to the order of j, a to the j, if and only if these greatest common divisors are equal. To prove this, we have this equality if and only if the orders of the elements are equal, but the orders of the elements from the previous theorem are given by these quotients. Because the numerators are equal, this equality is true if and only if the denominators are equal, and we get what we wanted. Corollary 3. Generators of a finite cyclic group. Let the order of A be n, then the group generated by A is equal to the group generated by A to the j for some integer j, if and only if the GCD of n and j is equal to 1. And the order of A is equal to the order of A to the j, if and only if the GCD of n and j is 1. This follows from the previous corollary by selecting j I, this I to be 1, and the GCD of n and I becomes GCD of n and 1, which is 1, and A to the I, A to the 1 is just A. Corollary 4. Generators of Zn. An integer k in Zn is a generator of Zn if and only if n and k are relatively prime. So Zn has as many generators as the numbers from 1 to n minus 1 relatively prime to n. Fundamental theorem of cyclic groups. Every subgroup of a cyclic group is cyclic. Moreover, if the cyclic group generated by A has order n, then the order of any subgroup of the group generated by A is a divisor of n, and for each positive divisor k of n, the group generated by A has exactly one subgroup of order k, namely the subgroup generated by A to the power n over k. You should read the proof of this theorem from the book. Corollary. Subgroups of the group Z sub n. For each positive divisor k of n, the set all multiples of n divided by k is the unique subgroup of Zn of order k. Moreover, these are the only subgroups of Zn. So you should try to list all subgroups of Z12, because the generators of Zn are determined by the numbers from 1 to n relatively prime to n. We introduce this number theoretic function, the Euler phi function. Phi of n is 1, and for any n greater than 1, phi of n denotes the numbers of positive integers less than n and relatively prime to n. From this definition, it is clear that the group Un has order phi of n. Theorem: the number of elements in each order in a cyclic group of order n is given here. If D is a positive divisor of n, the number of elements of order D in a cyclic group of order n is phi of D. Again, you should read the proof of this theorem from the book. The relationship among various subgroups of a group can be illustrated with a subgroup lattice of the group. This diagram, it includes all the subgroups of the group and connects a subgroup H at one level to a subgroup K at a higher level with a sequence of line segments if and only if H is a proper subgroup of K. Although there are many ways to draw such a diagram, the connections between the subgroups must be the same. And here we have the subgroup lattice of the group Z30. For each divisor of 30, we have one subgroup. The subgroup generated by 2 consists of all multiples of 2. The subgroup generated by 1 consists of all multiples of 1. So here we have all the numbers from 0 to 29. So this is the whole group Zn. The multiples of 0, this is only the trivial subgroup containing only the 0. Here the even integers from 0 to 28. Here in this group we have multiples of 6. Any multiple of 6 is even, so this is a subgroup of the group generated by 2. And this is a subgroup of the group generated by 1. This is the whole group. Here we have the multiples of 3, the group generated by 3. And here we have the multiples of 15. The multiples of 15 are 0 and 15 only. So the 0 subgroup is a subgroup of the group generated by 15, and this group is subgroup of the group generated by 3, and the group generated by 3 is a subgroup of the whole group Zn. And you have these other edges that describe the other connections of the subgroups.